Welcome back, everybody, to our continuing series where I go through the solutions to my spring 2020 final exam. In this problem, we look at another infinite series. We want to know whether or not it converges or diverges. There was some instructions also to find what one of the series converged to. In fact, the last video we made, where we looked at problem 9b, we actually did find such a one. In fact, we remarked in that video that the only time we can determine what the series converges to using our usual toolbox of tests is when we're using the geometric series test. Does not look like on this problem the geometric series test is going to apply. So we're simply going to try to determine whether this converges or diverges. All right, let's take a peek here. So I notice in both the numerator and the denominator, I have powers of n, and I'm just adding them together. And we talked in class about the intuition you should have on these type of problems. You should be looking at the highest powers of n. So in the numerator, my highest power is this 3n to the fifth term, and I really don't even worry about the 3. I'm just looking at this n to the fifth. And in the denominator, I get an n to the sixth. The 7/3 looks a little bit confusing, but remember 7 over 3 it's just 2 1/3, which is less than 6. So what I should be thinking is that this series should have the same property in terms of convergence or divergence as the series, well, we can start it at 4, it doesn't really matter a ton, n to the fifth over n to the sixth, right? I just ignore everything else. And of course, n to the fifth over n to the sixth is just 1 over n. And we know that the series for 1 over n diverges. This is essentially the harmonic series. Okay, it's starting a little later, but that doesn't matter. We know this diverges. Okay, either because it's a harmonic series, or we could say by the p-test, right, with p equal 1. So our intuition should be that this series diverges, and we want to use the limit comparison test in order to prove that. Now, in order to use the limit comparison test, we need to show first that the terms in the sequence are eventually positive, as are the terms in 1 over n, which of course they are. For this first one, it's because, again, as n goes to infinity, only the highest degree terms are going to be relevant, and they both have positive coefficients. So we know if we call this sequence a sub n, and we'll call the sequence for 1 over n b sub n, then we know that an and bn are eventually going to be positive. All right. Of course, the bn are always positive, but these ones may start with some negatives, right? You have to check individual n's, but it looks pretty likely. For instance, if n was equal to 1, you might get something. Of course, we're starting at 4, so hey, maybe we never have a problem. But I don't want to plug things in. I just want to observe in the long run, everything here will end up being positive because this n to the fifth will dominate. Okay, second thing, we need to show that this sequence, right, the a sub n's, are asymptotically equivalent to the b sub n's. So what does that mean? It means we need to look at the ratio of the an's to the bn's and show that this is equal to some positive constant. Okay, so this is what we want to do. So let's try it. So I'm going to take a limit, and I'm going to look at this first thing, 3n to the fifth minus 7n cubed plus 1 over 12n to the sixth plus 14n to the 7/3 plus 4. And I'm going to divide that by the nth term in my b sequence. Dividing by 1 over n will actually be the same thing as multiplying by n over 1. All right, so let's see, I can move this n inside, and I'll have a limit as n goes to infinity of 3n to the sixth minus 7n to the fourth plus n over 12n to the sixth plus 14n to the 7/3 plus 4. And at this point, I'm pretty happy because I have n to the sixth over n to the sixth in the leading terms. So I can multiply top and bottom by 1 over n to the sixth. And I'll now have a limit as n goes to infinity of, let's see, it'll be 3 minus 7 over n squared plus 1 over n to the fifth. And then in the denominator, I'll have 12 plus 14 times. All right, let's see. We're going to have to do 7/3 minus 6. 7/3 minus 6. So let's see, 6 is 18/3. So 7/3 minus 18/3 is negative 11/3. So I can do 14 times 1 over n to the 11/3. All right, plus 4 over n to the sixth. All right, and we can see now individually each of these pieces is very easy to check. As n goes to infinity, of course, 3 is constant. 7 over n squared goes to 0. 1 over n to the fifth goes to 0. 12 is constant. 1 over n to the 11/3 goes to 0. And 4 over n to the sixth goes to 0. Since we know each of these individual pieces converges, we'll know that not only will the sums and differences, but also the quotient will converge. In fact, what will it converge to? Well, 3 over 12, or a fourth. And this 1/4 is positive. And so we've done what we needed to do. That is, we needed to show that the limit of the quotient of the two sequences was some positive real number. And so now we know that our sequence AN is asymptotically equivalent to BN. And so at this point, we can use the limit comparison test. All right, so since the sum n goes from 4 to infinity of 1 over n, that's our BN sequence, diverges, the limit comparison test, the LCT, implies that the other series, the one that we wanted from the beginning, so this was our 3n to the fifth minus 7n cubed plus 1 over 12n to the sixth plus 14n to the 7/3 plus 4 also diverges. All right, so remember, limit comparison test is going to say if you have two asymptotically equivalent sequences, then their corresponding series will either both converge or both diverge. Since we know one of these series diverges, so must the other one. All right, hope that helps. Bye-bye.